All right, so welcome to the Chapel demo session. The topic of this demo is going to be on Chapel's Parallel I/O module. There will also be just some introductory material on the I/O module and Chapel I/O in general. So I'll be basing what I'm talking about today on this CSV example in this repository here, Chapel Parallel I/O examples. There's a couple of other examples in here. One is the 1 billion rows challenge, which is kind of a challenge that went viral recently about reading 1 billion rows of data from a file and then computing some basic statistics on those. So there's an implementation of that in Chapel using the Parallel I/O module. And then also FastQ, which is a genomics format that's kind of tricky to read in parallel. So there's a Chapel example of that. But we'll be just looking at CSV, which is kind of the simplest here. It's a pretty common file format where you just have several columns in a file separated by commas and then individual rows of data on their own lines in the file. So feel free to take a look at this repo. I'm going to get started just in a Visual Studio Code window here. I have a little bit of boilerplate code already set up. But basically what this is going to be is creating a CSV file of random color values that are just RGB values. And then I'll write a Chapel program that shows how to read those serially using Chapel's regular I/O stuff, and then a program that will read the file in parallel using the Parallel I/O module. I did not mean to keep that file. Okay, so what this color module is basically it just has one thing in it, this color record that has 3 integer values, some basic things defined on it. So a couple of initializers, a default initializer, and then one where you can set the value of the colors. And then I've defined a couple operators here. So you can add 2 color values together and then also divide a color value by an integer. We'll use this later to basically compute the mean color value in the file, just kind of as a sanity check and to compare the results of the serial I/O and the parallel I/O to make sure that we did everything correctly. And then there's a serialize and deserialize method. This basically tells Chapel's I/O system how to read and write one of these values to and from a file. So deserialize is expecting the value to be written in this format, so R, G, B. So it'll read an integer and then a comma and then another integer and so on. And then the serialize method does exactly the opposite thing and kind of prints it out in the same format. And then lastly, there's a random number generator that I've set up here, and then a factory method defined kind of statically on the color type to create a random color. So we'll use this to populate a file with random color values. So to start out, I will just create a new Chapel file just to create our CSV file. And then we'll create a couple of other programs to read it serially and in parallel. So the first thing that we'll want here is just the I/O module, and then also this color module with our boilerplate stuff that I just went over. And then we'll want to make this file be able to print out a variable number of colors in a CSV file. So in order to do that, we can use Chapel's config const. And this basically creates a variable that you can configure dynamically when you run the program. So let's just call this num lines. Start out with a nice round number. So by default, if we don't set this on the command line, this program is going to create a CSV file with 1,000 lines. And then in order to write to a file, we'll create a file writer. I'll just call this FW, and we can use this method provided by procedure provided by the I/O module called openWriter, and give it a file name. So we'll just call this colors.csv. And basically what this does is creates a new file or overwrites the file if it already exists, and then gives you a file writer handle to it. And a file writer is just a basically a buffered wrapper around a file that gives you a bunch of methods for writing data of various types into the file. So with this file writer, we can, let's start by writing just the header, so R, T, B, so that way someone looking at this file would know what's in it. And then just in a basic loop, we'll go ahead and write num lines, random colors to the file. So if we do 1.num lines, this is a range from 1 to 1,000 by default, where the second number is included in the range here. And then we'll do fw.write. Write can take a value of any type that's serializable, basically. So you'll recall in this this color file, we defined a serialize method. So write knows how to serialize a color value. If we didn't define this, Chapel's compiler will just auto-generate something, but the format would not be in CSV format like we've defined it here. So then we can do color.random and call that type method that I was talking about earlier. That's just going to create a random color value for us. And we want this to be right line, actually, so that each of them are on their own line. Okay, so I'm going to go ahead and compile this, see if I made any syntax errors. I'll pass the fast flag, which just turns on optimizations, essentially. If this compiles here, and then, oh yeah, we got a semicolon, okay. And then basically when we run this, it'll create a CSV file of 1,000 random RGB values. Once this finishes compiling. Okay, so now we have colors.csv. You can see all these triplets of 8-bit numbers. And then if we go ahead and run like num lines equals 20, get a much shorter file. Num lines equals 2,000, get a longer file. So now that we have that set up, we can go ahead and write a basic Chapel program for reading this file serially. And this is just kind of to give an intro into IO in Chapel, and then also to give us something to compare performance again to see how much faster the parallel version is. So just call this read CSV. And then again, we'll want to import a few things. Actually, maybe I should pause for questions before I move on here. Is there anything that needs to be clarified or any questions? Just make sure. Okay, cool. I will continue on then. Okay, so we'll want to use the IO module again, and then also use the that color module to the right. And then we'll also time this just to see how long it takes to read the file. So the time module in Chapel Standard Library has this stopwatch type that we can use for that. So basically what we want to do here is take, the name of a file that we want to read that's full of these color values, and then return an array of colors. So let's write a procedure to do that. So you do that with the proc keyword in Chapel, and let's just call that read colors, and it takes a file path as a string, and then returns an array of those color records. So basically the opposite of what we did with writing to a file with this open writer and then the file writer type that it gives you back. The IO module also has a file reader type, so we can do open reader and then just pass the path. This will throw an error if the file at that path does not exist. Otherwise, it'll give us a file reader, which is kind of the opposite thing. It's like a buffered wrapper around a file that gives us various methods for reading data from the file. So let's say that we know how many color records are in the file. and then we want to read them all into an array, what we might do is define our array, call it colors, and then define it over a domain from like 1 to 1,000. Let's say we know that there are 1,000 colors. This here is basically just saying this is an array defined over the indices 1 through 1,000. And then the element type is color. And then maybe we do something like for I in 1 to 1,000, fr colors at I equals fr dot read color. Or I guess this would be read line. They're each on their own line. So as with writing to a file, this is going to invoke the deserialized method on the color type and read each of these values in the CSV format that we specified. And then we would return colors. The tricky thing about this is, let's say that we don't know how many color values are in the file, which in general would be the case if you're doing IO in a lot of cases. You don't know how many values are in a file. So that makes this a little bit trickier. We can't just do a simple for loop into an array. So to get around that, let's instead read into a list. So we can use Chapel's list module, which gives us access to the list type. And this way we can just, as we read color values, we can just keep appending to the list until there aren't any more in the file. So instead of making this an array, we'll make this a new list with the color type. And then this way we can use a pretty common pattern with Chapel's IO module, where we create a color value. This will just be default initialized if we declare it this way. And then in a while loop, instead of a for loop, we do while fr.readline c. And basically this will just keep reading color values into this variable c until there aren't any more in the file. And then inside the body of this loop, we can just do colors.pushback c. So each time we read a new one, we'll append it to our list. And then at the very end of this method, we'll return colors.toArray, which is just a method on the list type that converts to a Chapel array. So we'll end up with an array of color values. Okay, so then basically what we want to do is read this into an array and time how long that takes. So we can use a new stopwatch provided by the time module, and then colors equals read colors, and then we named our file colors.csv. And then after we call the colors procedure, we can write out how long that took. So we can do s.elapsed, and that tells us how many seconds has a floating point value elapsed since, oh, I have to actually start the timer. So between s.start and s.elapsed, this will give us the amount of time that it took. And then, as I mentioned earlier, we're set up to be able to print out basically the average of an array of colors by summing all of them together and then dividing by the total number of colors. So we'll kind of use this as a sanity check to make sure that the serial and parallel versions of this program are doing the same thing. So in order to take the sum of an entire array, you can use the plus reduce operator applied to the array. And this will basically just start with the first value in the array and then sum them up in parallel and give you basically the total value of R, G, and B separately in a color record. And then if we divide by colors.size, this expression overall will give us the mean of that array. So that is reading a file in parallel. I'll go ahead, or in serially, I mean. Go ahead and compile this, again, passing the fast flag. to make sure optimizations are on. Yeah, Daniel, do you have a question?
Yeah, as soon as it says to compile, I was wondering what happens if the array is empty when you use plus reduce? Will it use some kind of default value, or will it crash?
I believe you'll just end up with the default initialized colors value. So we have this default initializer here defined on color that just sets RG and B to 0. And that's kind of used as the identity value, if I'm not mistaken, for the plus reduce operator. So you'll start with this and then add each of the array elements to it. So if there are no array elements, then you just end up with the identity value.
Cool, thanks.
Yep. Okay, so with that compiled, oops, we can go ahead and run it. Oh, that's right. I need to read the header. So we don't actually care what's in the header, so we can just call fileReader.readLine before we start into this while loop to read color values. So if we look back at our file here, there's this RGB on the first row. So that ends up not being able to be parsed by the deserialize method because each of these read calls is trying to read an integer, and RG and B are not integers, basically. So that's why we got that error there. Okay, so with that working, we print out the time that it took to read the file, and then also the mean value. And as you might expect with, let's see, 2000 random colors, the mean value is basically gray, where each RG and B can each range between 0 and 256. And so we end up with something right in the middle, which is basically a gray color, which makes sense. And then this time value we'll be able to use to compare with reading the CSV file in parallel to see how much faster we can get. So if we go ahead and create a separate program, let's call this one read CSV parallel.chapel. Basically, the first part of this program we want to be exactly the same as the serial version. So I'll just copy and paste this, except instead of calling this read colors procedure that we just defined, we're going to call one of the procedures in the parallel IO module. So we'll also replace the IO import with parallel IO, which is a package module in Chapel's standard library. So I'll talk a little bit now about what parallel IO provides. There are several methods in here for reading files like this that are full of a bunch of values of the same type in parallel. So read lines will just read each of the lines in the file as a string or a bytes. So that's kind of assuming that each line is just an individual string that you care about as a string. There's read delimited, which is what we'll use for this example, which basically separates the file by some delimiter that you provide to it, and then reads each of those items between the delimiter in parallel. And then read items is similar to that, except it's possible for the items separated by the delimiter to also contain the delimiter. So this is a less performant but more flexible version of read delimited, basically. And it's useful for things like this FASTQ example that I mentioned earlier. That's a bit of a trickier file format. And then there's also a couple of parallel iterators, read lines and read delimited, which behave like these first two. But instead of returning an array, they return just values in an iterator, basically. So you can iterate over all of the lines of a file or all of these items in a file separated by a delimiter. And then these three methods, there are versions that are meant for distributed parallel computations, and then versions that are meant for just parallel computations on a single compute node. I'm just running this example on my laptop here, so we'll use the single locale version, which is called read delimited as array rather than read delimited as block array, where block array provides a distributed array of values. So that's this method here. It's similar to the method that we just defined in that it takes a file path and then returns an array of some given type. But now it's generic over that type. So that's the second argument here, where you basically say which type of value do you want to read. You can define the delimiter. You can tell it how to handle the file header. You can tell it how many tasks to use, where by default it just uses the number of cores on the CPU essentially. So if you have like a 10-core CPU, it'll split the file into 10 chunks, and then each CPU core will read their chunk of the file in parallel, basically. And then you can also define this deserializer type. That's a little bit more of an advanced topic in the IO module, but there are various deserializers for different file formats. So like maybe if you wanted to read some JSON data in parallel, you could use the JSON deserializer, for example. But we'll just use the default deserializer for this case, so we don't need to worry about that argument. So basically what we're going to do is just replace the call that we had before to this read colors procedure with read delimited. And then we'll give it the file name, which is colors.csv. And then the type that we want to read is color. So that basically tells this generic method to return an array of color values. And then the delimiter is going to be new lines. And that's basically saying in this file here, each of the color values that we care about is separated by a new line. So that's how it's going to try to break the file up and split it across multiple CPU cores when it's reading. And then we also want to define the header. There's this header policy record in the parallel IO module that lets us do a few different things. In this case, we're just going to do skip lines 1, which says that we don't care about the first line, start reading after that. There's also options to like skip a particular number of bytes and things like that. And then just for fun, instead of using the default number of tasks, let's make another one of those config variables to define the number of tasks we want to use. And this way we can kind of explore how that affects performance. So again, if we do config const and tasks equals, just say 4 for default, then this will split the file into 4 chunks and read each of those in parallel, but we can use a command line argument to specify a different value, basically. So just to look at these side by side, basically the same setup here, except we're using this method provided by the parallel IO module instead of this serial IO code here. So if I go ahead and compile this, we'll be able to see how this works here. Really bad at semicolons today. Should take just a minute here. Okay. Now we can run the program and compare that to just read CSV. You'll see that we get the same answer for the average color. And then we're running slightly faster here. We can try just with one task, where in this case will probably be a little bit slower than serial IO. I guess we're kind of in the same ballpark here, where we're basically not using parallelism here because there's only one task. But just to show the performance benefits, let's go ahead and use a much bigger file. So make CSV file. We'll run our first program and then do num lines equals, let's try 10,000. I think we had 2,000 before. And then read CSV. So that took 0.016 seconds. And then if we do parallel, I think I have 10 cores on my laptop. So if we use all of those, let's see, that's about like a 4x performance improvement. I think we can see even more of a performance improvement if we make the file even bigger. So let's add another 0 here. See how long the serial version takes, about 0.1 seconds. And then if we go in parallel again, 0.02 seconds. I guess that's still about 4x, but as you can see, you get a considerable speed up. And I think as the file size increases, this becomes more pronounced. Yeah, so I guess about 8x speed up again here. And then the other thing to note about the parallel IO module is that one of the big benefits with Chapel particularly is using the read delimited as block array method, where if you're working with a file that's so big that it can't even fit in memory on a single computer, so then you're running some kind of simulation or something across multiple compute nodes, and each of those compute nodes just needs their own chunk of the data. You could use the read delimited as block array method and get basically one chunk of data deposited on each of the compute nodes and get much better performance than trying to do that in a serial fashion, because each of the compute nodes will read their chunk of the file in parallel with respect to the other compute nodes, and then also it'll use parallelism across the cores of each of those individual compute nodes. So that's kind of the gist of reading CSV files in parallel with the parallel IO module. Are there any questions or anything that needs clarification? John, go ahead.
I have questions, but should I don't know where the demo's going from here. Is there more to the demo? I guess is the question.
The next thing was just going to be kind of talking through the other two examples. I'm not going to re-implement the code or anything, but this was basically it for the CSV stuff.
Okay, I'll wait. I have questions about like what's going on behind the scenes, so I think I'll just wait to the end. Thanks.
Okay, cool. Sounds good. Yeah, so let me just talk through these other two examples real quick. Shreyas, do you know, we have another 30 minutes, right? This is supposed to be an hour. For anybody who has the calendar thing pulled up.
Yes, I believe you're right.
Okay, cool. Just making sure. Okay, so the other couple of examples other than the CSV one that I just talked about in this example repository are the 1 billion rows challenge and then reading a FASTQ file in parallel. I'll talk about FASTQ first. So let me show what one of these files looks like. This is basically a genomics data format that has a few different things in it. So basically one data point is 4 lines in this file. So the first line of each of these data points is just kind of a header with some metadata. And then the second one is the actual gene sequence. And then there's this optional third line where there could be like notes or other information. And then this fourth line, which when you decode this, basically gives a confidence value for each of these base pairs. So the machine that's reading the actual gene sequence, depending on how it goes, it can have a low or high confidence that like this was actually a G, for example. So maybe like $ means very high confidence, like it was sure that this was a G. So the reason that this is tricky compared to something like CSV.io is that it's difficult to come up with a clean way to split this file up in parallel efficiently. And the reason for that is that this fourth line can have an @ symbol, which is what the first line is supposed to start with, a plus symbol where that's what's happening here, what this third line is supposed to start with, or any of these letters. So like if naively we were to say we should split the file wherever there is a new line and then an @ symbol, because the first line of each of these FASTQ records is supposed to start with a new line and then an @ symbol, basically. We could end up accidentally splitting the file here because there's nothing preventing this fourth line from also starting with an @ symbol, basically. So because of that, the parallel IO module has this other method that I mentioned, the read items as array, where you can say that the delimiter is new line @ and it will look at the file and try to split it up that way. But before it moves on with that decomposition of the file, it actually double checks that you can successfully deserialize a record starting at that offset. Whereas the method we used for CSV just looked for a new line and just assumed like, okay, I can start reading a color value here because we just found a new line. And because of that, let's see, this FASTQ file here is kind of the boilerplate for this example, kind of like our colors module. Because of that, the deserialize method needs to be designed to throw an error whenever it fails to properly deserialize a value. So there's a couple checks in here that are saying, like for example, if the sequence size and then the quality size are not the same, then we must not have properly started at a proper offset when trying to deserialize this value. So that might be a little bit into the weeds, but I think it's good to know that this method exists because there are some file formats where this read items as array method is helpful because they're tricky to split the file up and spread it across multiple compute nodes or cores. Are there any questions on that one? Okay, cool. And then the last one, probably the most interesting example, is this 1 billion rows challenge, where basically the task is to take a file that looks like this, except with 1 billion rows instead of 10, where each line of the file has the name of a weather station somewhere in the world, and then a semicolon, and then a temperature reading. And the task is to parse through this whole file and basically output the minimum, average, and maximum temperature at each of the weather stations that were in the data file, where in a lot of cases there are repeating weather stations. So you have to do some kind of a map reduction operation to gather all of the temperature values for each of the weather stations and then do some statistics on those data to print out the minimum, average, and max. So again, this example I set up with kind of this boilerplate module that has a couple of useful types in it. There's this temperature statistics record that has the minimum and maximum temperature value you've seen so far, and then the total and count, which you use to compute the mean. So this is what's used basically to keep track of the data as you're parsing through the file. And then it has some operators set up for kind of merging these. So when you add two, the minimum becomes the minimum of both values, basically, etc. And then when you serialize it, you get kind of the standard output format for this challenge, where it's like minimum / mean / maximum. And then there's also this city temp record, which represents what the data look like in the input file. So there's the name of the city and then the temperature value. And so there's a deserialize method where you basically read a string up to the semicolon. This is a method provided by the file reader type. And then you strip off that semicolon and just save the string as the city name. And then next you read a real value as the temperature. Yeah, so these are kind of the types that support being able to do this computation. show what the serial version looks like for context real quick. So as before, we're importing the IO module. Instead of like a list like we did with the CSV example, we want to map so that we can combine temperature values from weather stations that have the same name. And then we're using that temp data module that I just showed. And then basically we'll open up a file reader, create a map of the temperature station name to that statistics record that I showed you with min, mean, and max. And then we'll do the same kind of while loop thing we did before. So while we're able to read one of these city temp records on each line of the input file, we will accumulate those data into the map. So if the map already has a city with this particular name, then we add the temperature statistics to it and kind of accumulate those in there. Otherwise, we add a new record to the map if we haven't seen a weather station with this name before. And then at the very end, we just print out the statistics, and that gives us the output that we're looking for. And then, so the parallel version of this is a bit more complicated. Here, this 3-line thing here basically is the kernel of the computation. So instead of reading the entire file into an array as before, we use one of those iterators that I was mentioning, combined with Chapel's for all loops. So this is a parallel loop where the body of the loop can happen in an order independent manner. So the for all loop kind of splits the computation up across multiple cores. So what this will do is just in parallel start yielding city temperature values from the file, where again we specify the delimiter, so that's the new line. We specify the number of tasks, so kind of similar to those methods I was showing earlier, except it's being consumed by an iterator. And then this is a bit more advanced Chapel, but on each task that's being used in this for all loop, we create this map reducer object. I'll explain that in a second. And then with the map reducer, we basically do that same accumulation operation that we were doing in the serial case. So if it's a new temperature station we haven't seen before, we just keep track of it. Or if we have seen it before, then we kind of accumulate the statistics and update the minimum and maximum and all that. And then at the end, we print out this global city stats map. And then, so basically this map reducer thing is basically there so that each of these tasks can cooperate with each other while they're updating this global city stats map. It's a little bit outside the scope, I think, of just talking about parallel IO, but I'll just give a rough overview. Each of these map reducers has a handle to that, basically a shared handle to that global map. And then also it has its own local map. And then as you do these add or update operations, it does the same thing that we did for the serial code, updates the local map. And then periodically it obtains a lock to the global map and then flushes the data to that global map. So each of these tasks kind of involved in this for all loop are concurrently and independently reading into their own local maps that they're not sharing with the other tasks. And then once those get full enough, they are dumping them into the global map and kind of doing that in a concurrently safe way using a lock so that only one task is accessing that global map at a time. But yeah, some of the details of this are a little bit outside of the scope of just talking about parallel IO. So I can go into details if people have questions, but otherwise I think I'll leave it at that. Are there any questions on the 1BRC example here? If not, John, I think we could go back to your kind of higher level question that you had. Oh, Daniel, go ahead.
Actually, never mind.
Go ahead, Daniel. Don't be
No,
shy.
never mind. I changed my mind.
All right, so some of my questions are answered by looking at the parallel IO documentation while you were doing this here. So I used to do work in IO and I used to do work in genomics. I'm afraid I can just monopolize this conversation. So I really want to make sure other people have an opportunity to ask questions first.
We will interrupt aggressively if need be, but please go ahead.
So, so let's talk about the single node case, which is what you're running right now. I'm surprised to see such a large performance benefit from going from one task to many tasks. Do you know where the time is going? And I say that because if you're reading the file off of the storage device, I would think that would be the bottleneck. And so I'm kind of wondering or worried that when you create the CSV file, it's in the file cache. And so I guess the first question is the file being M-mapped or is it being read from the underlying file?
I think on macOS, at least, it's not being M-mapped by default. Where I think we can provide hints to the IO system, as you know, to indicate that we want to use mmap, but I don't think that's happening by default on macOS.
So, well, first of all, I should have had a disclaimer. I think this is awesome. When I joined the Chapel team, I was kind of surprised, I'll use that word, that we had no support really for parallel IO. And that's not a problem if you're, in my mind, that's not a problem if you're mainly doing simulations where you have a fairly small state that you're reading in and then churning away for hours, then spewing out, a fairly small bit of output. But in things like the genomic work you're doing, a lot of these files are too big to fit in memory. And the actual computation you're doing is fairly minimal. What you're really trying to do is just churn through tremendous amounts of data. So I'm really happy that you took this on. And I kind of shied away from it because it's a gargantuan task. But anyway, I just wanted to say I appreciate it. But I'm a little bit worried that what you're measuring is the bandwidth to sort of do memory copies, like copy out of the file buffer into whatever format Chapel has for the colors in memory. So I would just be curious, like where the time is going. And in my mind, if we are interested in these like huge input files that don't fit in memory, then what we're really worried about is like the speed. Like if you were to run this on a single node on one of the machines that has a Lustre file system and sort of ensure that the file's in Lustre, not in the file cache, I'd be curious what the performance benefits are. So that's not a question, that's just an observation.
I have done some performance testing on Lustre file systems and seen pretty significant performance improvements, more so than I'm seeing here.
Okay, then I guess I'm wrong about that. Because I guess if the file is big enough, then you're going to start reading the blocks of the file in parallel, and you're going to get a benefit from that. Although I would expect the file system to be doing like read ahead, even in the single task case. So I don't know enough about Lustre to know, how that works.
Yeah. I mean, I think some of the benefit here is just like you were saying from parallelizing the work of actually doing this deserialization here. Where if you have multiple tasks kind of doing this on their own chunk of the file, then you're, seeing concurrency benefits from, doing a bunch of this work in parallel, rather than just streaming through the file in serial and, deserializing one at a time. And then I think that the one other thing that's making this not a super fair comparison is the, the serial version. There's some overhead involved in using a list here and, pushing onto the list where, occasionally we have to reallocate memory and double the size of the list, basically, is what's happening behind the scenes. So there's some overhead there.
Okay. But when you create that, when you run make CSV file, that file is going to be in the cache. And it's certainly going to be in the cache after you run read CSV. So read CSV parallel might be benefiting because the files, if it is already in the cache. So
Yeah.
depending on what you're trying to measure, you might want to flush the cache after you run make CSV and after every run of the, excuse me, my voice is screwed up today. Every run of, reading the file.
Right.
And unfortunately,
Right.
there isn't like a general way in Linux, I'm sorry, in Unix to do that. It depends on your flavor.
Mhm.
Then the other thing is, well, you do have the low-level routines to like, it returns an iterator that returns the lines of the file, because the other thing you might want to do, a person might want to do, especially with your genomic example, is you don't really want to store those reads as ASCII characters, right? There's only 4 characters, and so that's a white lie. But in the ones you have there's only 4 characters, so you obviously can store them as 2 bits. And if you're dealing with very, very large input files, you're going to want to try and compress that. So, so that's another comment, not a question, which is it's nice that you have that low-level routine because it allows people to like transform the input into some internal form instead of just getting an array of the whole thing. Well, I guess that's what the deserialized does, right? I'll take that back. Deserialized could do something with encoding.
Yeah, that's a good point. Where I'm doing something pretty naive here and just storing strings and bytes. But yeah, in here you could definitely do some encoding and compression and stuff. I'm just doing kind of the simplest possible thing.
Right. So yeah, okay, so that's cool. All right, so and then in the distributed case, like imagine I have a bunch of nodes and I want to process this file. I probably don't want to have them kind of do each line of the file or each read in the file in like round robin or something like that. I want to read one block of the file into one node and then have it process on that node, all the lines in that block. Is that something that does the read lines iterator work across multiple nodes?
In Chapel 2.1, it does not, but that should be coming in for 2.2.
Okay, I was looking at 2.1.
Yeah, so there's going to be this target locales argument, where by default it just executes on the calling locale and doesn't do any multi-locale stuff. But you could specify the locales array or whatever here, and then it would first split the file up blockwise across locales, and then within each of the locales there would be some concurrency also.
All right, so if I have 2 locales, then like the first half of the file is going to be on the first one and the second half is going to be on the second one. Is that the idea?
Yeah.
With a little bit of like fudging in the middle for lines that span the break for
exactly.
All right, cool. All right, that's very cool. All right, yeah. So if I looked at the 2.2 documentation, it would have answered my question. All right,
no worries. That's awesome. A good plug.
I like it. That's all my questions. Or I didn't even ask a question. Those are my comments. Sorry.
No, those were good observations. Because I'm definitely not coming from a scientific perspective of having used this stuff a whole lot. So it's definitely good.
But I do think just one of my points is like we do want to think about files that are too big to fit in memory, period. Like I don't care how many nodes you have, how much memory you have, it doesn't fit. So in that case, it's kind of a streaming paradigm where you're working through it and coming up, doing the computation as you go.
Right. Yeah.
All right.
Thanks. Yeah, and I think that's what the iterators are useful for sure. But,
yeah, that's cool. I'm gonna try this out some point when I have all my spare time.
Sounds good. All right. Are there any other questions or comments? If not, I think we can go ahead and adjourn. So thanks for joining, everyone.